So thank you for being here. I'm going to talk to you about quantum coin flipping and an experimental implementation that we did using a plug-and-play system. So the partners of this implementation in theory are all these institutions. So what is coin flipping? We basically have two players, Alice and Bob. They're separated by some distance and they want to flip a coin. They have a communication channel, and at the end of the protocol they just want to agree on a common bit value. So why do we need coin flipping? The version that I'm going to present is equivalent to doing bit commitment, and it can be used to do leader election, zero knowledge protocols, or secure identification. Just some definitions on coin flipping. If Alice and Bob are both honest, then what we want from the protocol is to have equal probabilities of outputting coin 0 or a coin 1. Now, if Alice is cheating and Bob is honest, then we define the cheating probability of Alice to be the maximum of her probabilities of forcing the coin to be 0 or 1. And similarly, when Bob is cheating and Alice is honest, then we can define the cheating probability of Bob to be the maximum of the two probabilities. And we can upper bound this, we can define a bias epsilon such that we can find an upper bound of these two cheating probabilities. And we define as the cheating probability of the protocol the maximum of these two cheating probabilities. So in general, what we want is we want the protocol to be fair for the two players. So we usually want these two probabilities to be equal. Okay, so some history on coin flipping with information theoretic security. We already know that classical coin flipping is impossible, so cheating probability is always equal to 1. Now, we also know from the no-go theorems of bit commitment that it's also impossible to have perfect quantum coin flipping from Myers and Low and Chow. So the cheating probability, the quantum cheating probability is always bigger than half. Now, we can have some non-perfect protocols. There have been several non-perfect protocols that achieve cheating quantum probability with an upper bound of 3/4. And in 2003, Kitaev proved using semi-definite programming that we actually cannot do much better. There is a lower bound on the cheating probability of 1 over square root 2. So there was a gap between these two values, and finally in 2009, Sheyu and Karenidis managed to bridge this gap by using Moshon's results on weak coin flipping. Okay, so in general, when we want to implement a coin flipping protocol, we need to take into account several practical considerations. So for example, what is the technological state of the art? How are the states that we're going to use, how are they generated? We also need to think how does our protocol how does our protocol behave with system transmission losses and noise, and similarly with dark counts and finite quantum efficiency of the detectors. And finally, we need to see how our protocol, if our protocol needs, first of all, quantum memory, and if the adversaries with quantum memory can use their memory to increase their cheating strategies. So some of these things have already been considered. For example, we have some loss-tolerant protocols by Berlin et al. And Seiyuu with these respective cheating probabilities. And we have also some implementations, with the latest one being that of Berlin et al. In 2011, where they use this theoretical protocol, but instead they use an entangled source to do coin flipping. Okay, so our protocol will be based on the theoretical work of 2009, and we're going to be using k-states phi. These states are chosen using a basis alpha I and a bit ci. So we have a set of 4 possible states. They are actually kind of rotated BB84 states. So the states that we're going to be using are the colored ones, these 4 ones. And they also can define 2 measurement bases. So as the red one is, for example, the 0 basis, and the blue is the 1 basis. Okay, so our protocol goes as follows. Alice needs to choose k of these states. So she needs to choose one out of this possible set of 4 states. And she sends these k states to Bob. And Bob chooses at random his measurement basis, and he measures all of the k states. Now, since we have some losses in the channel, he might not be able to measure all of the k pulses. So suppose that the first measured pulse is the jth pulse, and the outcome of his measurement is the C prime j. So he lets Alice know the index of the first measured pulse, and he also lets Alice know a random bit b. And then in the third step of the protocol, Alice reveals to Bob which state was used for that jth pulse. So she sends the basis and the bit that she used. And of course, if the basis, the preparation basis and the measurement basis are the same, then the outcome, the preparation bit and the outcome of Bob should be the same. So if it's not, then Bob aborts. Now, in all other cases, the coin flipping protocol succeeds, and the coin is the XOR of bits of the bit of Alice and the bit of Bob. The properties of our protocol is the following. We do not need any entanglement, so we use a simple attenuated laser source. We do not need any quantum memories, and we can tolerate some losses and some noise. Now, due to this tolerance of losses and noise, we also need to allow our honest players to abort sometimes. So the security analysis of our protocol goes as follows. We've got some protocol parameters that we need to know. For example, the mean photon number per pulse mu, the number of pulses that we use k. Now, this is the y is basically the state coefficient, is how rotated our states are. Now, the dark counts of the detectors, the channel noise, and the losses of the channel. Okay, so we can analyze the probability of honest players aborting, and we can split it in 3 different events. So the first event that might happen is that the detectors of Bob do not click in any of these k rounds. So this might be due to losses in the channel, and that no dark count has happened. So dark counts are basically random clicks in the detectors that do not correspond to any real pulse having been sent. So the second event is that the first detection is due to a dark count. So this means that all the pulses have been lost, but there was a dark count detected. So this will lead to an abort with 1/4. And then the last event is that the first detection is actually a result of a real pulse, but the noise in the channel has resulted to a different outcome than the one that was sent. Okay, so then we can analyze the dishonest Alice. So when Alice wants to cheat and she wants to force a specific outcome of the coin flipping protocol, what she needs to do is she wants to be able to reveal either 0 or 1, depending on what Bob sends in the second step. So because Bob decides to send at random a bit, then Alice wants to be able to reveal 0 or 1 at the same time. So the cheating probability of Alice only depends on how we build the states. So it only depends on the state coefficient and the distance between them. Now, for dishonest Bob, his cheating probability depends on the distribution of the number of multiple photons in the pulses. So when Bob gets only one photon in a pulse, then it's easy to analyze his cheating probability. It's just he wants to distinguish between the state that corresponds to bit 0 and the state that corresponds to bit 1. But when he gets more than 1 photons in a pulse, then he can do a more sophisticated measurement, and he can also use this multi-photon pulse in order to increase his cheating probability. So his dishonest strategy basically depends, his dishonest probability depends on how many pulses we send, how many photons are in the pulses, because this might increase the multi-photon pulses, sorry. And it also depends on the state coefficient. Okay, so for the implementation, we use the Clavis2 system of ID Quantique. This is actually a plug-and-play system because the laser source is at Bob's side. So what is happening is that Bob is sending some pulses, and they get splitted by a beam splitter and they pass through a long arm here and a short arm. Then they go in Alice's system. They get reflected by a Faraday mirror, and then on the way back, Alice chooses which state she's going to send, and she also applies some attenuation in order to choose the mean photon number mu that exits her system. And then on the way back, they go on the other way around through the long arm and the short arm. Bob applies his measurement basis here, and according to the interference in the beam splitter, then we get a click in detector 1 or detector 0. So the Clavis2 system is used for QKD, so it's used for key distribution, and it was not straightforward to do the coin flipping protocol. What we needed to do is we need to do some hardware and software enhancements on the system. So the hardware change that we need to do is we basically need to replace the detectors with high efficiency and low noise ones in order to be able to see any quantum advantage for any distance. And we also needed to do some software changes because we didn't use the BB84 states as in QKD, but we needed to use this rotated states. So we need to be able to set the coefficient y both in Alice's box and in Bob's box. And another issue was that we were attenuating very much. So the mean photon number per pulse that was exiting Alice was very low, and this was hindering some of the procedures in the boxes. So we needed to reprogram the software. Now, maybe most importantly, we also need to adapt the security proof. So it's very common that 3 assumptions are usually made in security proofs. The first one is that Alice can create its state with equal probability and independently of Bob. So she can choose one of the 4 states that she wants to use at random. Then the second one is that Bob can also choose his basis and his bits uniformly at random and independently of Alice. And then the third is that Bob's detectors have the same detector efficiencies. So the first 2 actually depend on the quantum, the random number generators and on the phase modulators, and they're relatively low. So the variation on the from uniform, the deviation from uniform is very small. So we didn't need to do any correction for this, but we incorporated in our errors. And the problem was that the detectors of Bob had different efficiencies, and the difference was quite high. So what we did is that we used a very smart procedure that's called symmetrization of losses that Stephanie Venner and her co-authors had introduced in their noisy storage bit commitment scheme. So what Bob had to do is that he had to make his detectors equal. So he had to throw away around 32% of his detection events from one of the detectors, from detector 1. What we have from our experiment is the following. You can see here this graph of cheating probability versus honest abort probability. So this is a classical line. This is a classical bound where it's been proven that no classical protocol, coin flipping protocol, can be below this line. So all the classical protocols are above, in this area above. So what we want is we want to have a quantum protocol that is below this line. And we actually managed to show that for 15 kilometers, we managed to have this quantum advantage, while for 25, we fall a bit short of showing the same thing. And this area here is basically our errors that were introduced by the problems that I explained to you before. So we can see the same thing by introducing this gain function, where the gain function is just this difference between, this distance between the classical limit and our quantum results. So we want to have a positive gain in order to show some quantum advantage, and we managed to show this for 15 kilometers, and here is a 25, which are below the classical classical bound, let's say the 0 advantage. And just for comparison reasons, I also show you here the the previous implementation that Berlin et al. Did in 2011. So we can see some stringly stronger than classical security, and this has happened with a practical system, an off-the-shelf equipment that is readily used with the small changes that I discussed previously. But so if you can see in the previous picture, you can see that that the cheating probability is relatively high. It's above 90%. So this is an inherent property of the protocol, because even the theoretical protocol has a 90% limit. So we can show information theoretic security, but we have a cheating probability that is relatively high. On the other hand, there have been some coin flipping protocols against bounded adversaries where the cheating probability is almost perfect. Now, when we say bounded adversaries, these can be, for example, computationally bounded or noisy storage, for example. And it seems that there are these two levels of security that we may need to choose from, but actually we can combine these two, and we can have some combined protocols where the security of our coin flipping protocol can lie on top of the perfect security of these bounded protocols, and therefore add the security guarantee against unbounded adversaries as well. So what this means is that the bounded protocols were secure against bounded adversaries, but when the adversaries if the adversary, for example, could invert one-way functions or had a perfect memory, then these became totally broken. While with the compiled protocols, even for adversaries that are unbounded, then we can also have some security, which is relatively bad, but it's still less than 1. So what I've shown you is that we can have a coin flipping protocol that is secure theoretically, and we can have experimental demonstration with security guarantees which are strictly better than classical. And we can do this with present-day technology. It's easy to do. We just plug the boxes in the electricity, and we can do a coin flipping protocol. And we also have some security proofs that take into account all standard imperfections like asymmetries in detector efficiencies, multi-photon pulses, losses, and noise. So there are still some open questions that are very important. For example, can there be some side-channel attacks or some other types of attacks on the plug-and-play system? There have been previously reported many attacks, like the blinding attacks, that could attack the plug-and-play system. So it's very important to study these types of problems. Then can we maybe use decoy states or some kind of error correcting codes in order to increase the security or the performance of our protocol? And can we further study other types of bounded adversaries, like for example bounded storage or some other types of adversaries that can be computationally unbounded, but they can maybe not control the losses of the channels, or we can do some more sophisticated analysis. Okay, so this has been a work joined with Paul, Tom, Andre, Mathieu, and Patrick from ID Quantique, and Jordanis and Eleni. And this is theoretical analysis that appeared in 2011, and the experiment appears in this this publication if you want to have a look. So thank you.
So in the experiment, you mentioned you update the plug-and-play system by using new detectors. I'm just wondering, what are the parameters for the detectors, and what's the requirement for this kind of detectors?
So I said that we replaced the detectors, but we didn't use any type of really high efficiency detectors. We just upgraded them a bit. So the detection efficiencies were less than 10%, basically. One of them, I think, had 7.7%, and the other 5 point something. So I think the most important part was that we needed to decrease the dark count. So we needed to run them in very low temperatures. But one of the things that might increase, that I think would definitely increase the performance and the channel length that we can do our protocol, is using much better quality detectors.
Okay, maybe I can quickly ask something about, does your protocol have cheat sensitivity? So can you tell when someone else is cheating, or what, do you have any comments to say about that?
So it depends. So if the attacks, if for example they try to do this type of like blinding attack, then it depends on the technology of the system, the plug-and-play system. So they have this intensity monitor, for example, that should be able to detect this type of things. But since it's since whatever is happening in Bob's detectors, then he might try to, let's say, optimally distinguish the states. So we cannot really know if he's trying to guess the bit or not. So it's not in the theory, but it should be able to happen, and we should be able to detect any side channel attacks. I mean, in theory again.